You may want the triangle count. Something like that. And maybe all you want to say is this is small. Can you prove that in this region all optimizers are constants? That's not very hard to prove, because after all you can use Lagrange multipliers. You have something like something like that. Or you can make it lambda by 6 and put a 1/6 here, whatever it is. You want to minimize something like this. So this is fairly explicit, and you can write down the Euler equations for the variation problem, which looks like something like this. Integral fxz fzy dz lambda equals log f over 1 minus f minus log p over 1 minus p. I'm just manipulating with it. It's not hard to show that if if lambda is sufficiently small, you can show that in this case lambda will be small. C small implies lambda small, and if lambda is small, only constant solutions are available for this. That's but then you have no control on how small it is. What you get is may not be the right thing. Okay. But it has the advantage, it covers both sides. So the other argument to show that sometimes click is better than simply increasing the number of edges. Let's look at P small, and you want T triangles. And you can compute, if you are limited to ER graphs, what you need is roughly how many edges you need. You can work out. It's ER graph, so the probability should be, you want the probability to be 60 to the 1/3. So basically the entropy of Bernoulli 60 to the 1/3 to Bernoulli P, but P is very small, so it's very large, and if you compute it, it'll be log 1 over P with a constant C outside. You can compute the constant explicitly. It's not a hard problem. On the other hand, if you are allowed to form click, sorry, this is also log. I forgot to put the log in. There should be a log here too. Okay. So the only question is CT and C prime, which is bigger, which is smaller? C prime is 60 to the 2/3 log 1 over p, if you compute. That's because the way you count edges in a click as opposed to, just Bernoulli edges. Ct on the other hand, 60 to the 1/3 log p. Since 60 is less than 1, Ct is this is bigger, C prime t is smaller because it's 2/3 power. So it's better to form a click. Of course, this is only asymptotic as p goes to 0. So if you have p is sufficiently small, you tend to have a click rather than just increase the number of edges. C prime is less than C. So you can do an analysis of the variational problem in general for these graphs, and the regions where constants are the best is determined by the convex minorant and not hp to the power x to the 1/3, which is what we did, but to the power 1/2. Well, 1/2 or 1/3, it doesn't matter. You have a convex minorant, something below, and you look at where they touch, the result is the same. But the function to which you are trying to find a convex minorant, if you use this function, the result is exact. So if they don't touch, the minimizer is not a constant. Okay? This is exact. It's a result due to Levetsky. Triangles can be replaced by any regular finite graph. And then, if d is the degree of the vertices, the convexity is decided by x to the 1 over d. And for the triangle, d is 2. Okay. This is again an exact result. Then there are things called exponential families. These are change of measures, like in statistical mechanics, where you change the measure by n squared times, you throw in a function of the graph there, and then you compute the get a partition function, the log of the partition function is subtract. And f should be something that's continuous in the cut topology. Could be the triangle count, could be the count of some other finite graph, would be a combination of the two, anything of that nature. Now, what happens to this is standard large deviation theory, more or less. Once you have the large deviation theory, to analyze this is fairly easy. The normalizer psi n, Fg can be number of triangles, the usual LP-related conclusions, the measure is concentrated on the minimizers, and the variational problem you have to solve is this. You have the entropy on the graphons, you have the function f defined on G extended to graphons, and you take the maximizer of this. If you get G to be unique, the limit, the graphon, most of the weight will be on graphs whose graphon looks like the maximizer. Or if you, and anything away from it has exponentially small probability, and the rate function is just the difference between the two rate functions. That's the standard then the next group of ideas here is sparse graphs. Okay. So far we have looked at graphs that are rather dense, because the number of, okay. So you can ask yourself, what happens if like the original problem of Varadhan and Renyi, the probability of a graph of an edge Pn was a constant over n, and he looked at what happens when the constant changes. That was his original work on random graphs. Now to do large deviations, C over n is not good enough, but one believes that one must necessarily have npn going to infinity. Okay. So the game is, how much can you improve? Okay. There are various types of results that are known. The trouble is there is no general Shemiridi lemma here. So one has to use ad hoc techniques in order to do the estimation. And roughly, it's clear there is n factorial in the background. So your rate function better be at least n log n, otherwise you are going to get into a fight with n factorial and it's not clear who is going to win. Okay? So there are various alternatives. You can look at Pn bigger than log n over n. Or you can make life a little easier by looking at Pn to be n to the minus some constant c, c less than 1. And then in all these cases you can ask for the type of question you want to ask, or what is the probability that the triangle count of the graph is bigger than some 1 plus delta times its expected value. What is the probability of this? This is so-called upper tail probability. And you want to get for this probability both an upper or lower bound in terms of some exponentials. Okay. So originally when people started, they got appropriate powers of n on both sides, depending on what power they put here. But they had log factors on one side and didn't have log factors on the other side, though didn't really match. And then there was further improvement where they got rid of the log factors and the powers of n matched, but the constant was two different constants, one above and one below. Then there was further research and the constant was matched. And all this required different assumptions and different conditions and so on. Okay. So I'm not really familiar with all the details of this. There are various expository articles, one by Saurabh, which was done a year ago. And I think it's in Bulletin of the American Math Society or someplace, which is a good place to look at them. So I'll just give you a sample of these results. Partial results are known, and one always wants Pn to be at least this much. Is the type of result. But here you have p square log 1 over p, but it's the same on both sides, but C1 and C2 are different. Here there is really a log, you need it. Finally, the correct constants are worked out with additional conditions. Okay, that was the last of my slides, and I will answer questions at this point, because there's not much more I can say about random graphs. There's other one thing I could say, which is you can look at random matrices. Xij, say symmetric matrices and your eigenvalues. A lot is known about the largest eigenvalue. The largest eigenvalue, say these are all standard 0, 1s or something like that. The largest eigenvalue is some C root n. And one even has some large deviation results that is much bigger than C root n by C prime root n or something like that. And the large deviation probabilities are like e to the constant times n. They're not still really real large deviations. They're, one should call them moderate large deviations, because you have n square independent random variables. So real large deviations will involve e to the minus n square times something. Okay, so let's compute the probability normalized by n. These delta functions they converge or normalize to some sigma 1, sigma 2, sigma n. So this is the first largest, this is the second largest, and this is the one. So in n scale, you have a few. Maybe you have a few, may have more than few. What is the large deviation probability of that? You expect the large deviation probability to be of the order e to the minus n square times something. Okay. So there is, it looks like it want to be made into a graph form. Why not? It's not 0 and 1, it's something non-negative. Assume it's bounded, for example. You can chop it up into a finite number, and there are versions of Shemaredi with colors. So you have a finite number of colors and so on. So there's a graphon theory for these too. So you think of graphon theory, you get a function kxy. And the large deviation rate function for k is just exactly the same as you compute the Sanau, Kullback-Leibler type information for something, for, and that's what determines kxy is. Okay, and then kxy is a symmetric kernel. Under suitable assumptions here, you can show that the rate function is finite if and only if this is a nice compact operator, trace class, Hilbert-Schmidt, or something like that. Then this will have eigenvalues. Okay. And then you project onto this. So the large deviation rate function for this is a contraction of the large deviation rate function here through the eigenvalues. So this is just like random graph, but with a little complication thrown in. But it requires some serious assumption which excludes Gaussian. The reason it excludes Gaussian for you have to truncate at some point because you have to chop it up into colors. You can't chop up an infinite interval. You have to chop it, throw away something. So you have to handle what's left. Turns out in order to handle what's left, you need the assumption that the expected value for the individual random variables e to the lambda mod x square should be finite for all lambda. So it just has to be sub-Gaussian. Because Gaussian still, in the n square entries, there could be one entry which is too large to mess things up. Okay. And that seems to be the problem. Okay. Okay, now we'll take questions.
This problem is you expect only at the level of matrices, but at the level of eigenvalues you expect result also for Gaussian?
No, the point is you have kxy, right? You want kxy to have eigenvalues and so on. So you need to compute certain things, and so you need to compute exponential of some traces and things like that in order to get a reasonable estimate, and that requires some exponential moments. It turns out Gaussian just misses it. It's possible that further analysis could provide some way of handling it, some special way, but I didn't pursue it.
Is there a reference for this?
Early Emeritus joint paper with Saurav. I only have 2 joint papers with Saurav, and this is one of them.
So the maximum eigenvalue, you said, has a deviation which is of e to the minus, the probabilities are e to the minus c.
Yeah, see, the normalization is such that in the end, the zero graphon is where everything is going. So any movement away from zero has probability e to the minus n squared in the scaling. Okay? So if you want to go to a kernel kxy, it has some rate. And you can specify in fact the entire spectrum. And what you need is k's with this spectrum, and you minimize the rate function over all k's which have this spectrum or whatever properties you want to the spectrum. The spectrum is one thing, because when you do k, the kernel, and make it measure pursuing transformations, for example, then what they're all unitarily equivalent. So they all have the same spectrum in some sense.
I had another question on the case where you're looking for triangles T and there's a mixture that determines the right way to get the deviation.
Which one?
Each p hat of
The mixture 1 minus.
1 minus delta times f. And
That doesn't get you the right one. That tells you improve it, just gives you a bound. That may not be the right one.
but the mixture is of 2 constants. Is that correct?
No. See, you give me an f, your candidate, then I mix it with a constant.
Mix it with a constant to improve and say that it's not, you can do better than just one constant.
No, you give me any function, I can do better. It's not just enough to say I can do better than any constant.
Yes.
I should do better than any function.
So this mixture, eventually the right mixture will be a mixture of 2 constants. Is that
Depends. In many cases, the optimizer could be a mixture of several constants.
in this case we are viewing it as a function of only one variable. So there must be that perhaps you can get
No, in the region where the function doesn't touch the convex minor end, all I know is constant is not, one constant doesn't work. That's all I know. Maybe it's 2 constants, 3 constants. I think there is some work by physicists where they have mapped it all out, and it looks like there are various phenomena. See, there's a nice picture that's sort of what they call the phase diagram. So there is P here, there is T here. Okay. And here is the some line. There's some region like this. Okay. And here it's a constant. Here it's not. So when you start here and go up, initially you have a constant. Then for a long time, you don't have a constant. Then at the end you have a constant again.
I think I understood where I had. So I was thinking in terms of HP of t alone, but you must look for in the space of all functions.
Yeah, exactly.
So then, because this is much bigger space, would have several mixed states.
So, did you also say that for large enough P there is no phases? I mean, it's just constant.
There's no. It's not P, T large enough.
No, if you take a P large enough on the right,
Yeah, if P is large enough, you got as many triangles as you want, why fool around? If you have P large enough and you want very few triangles, then you are in trouble. Right? It's a question of where you go. This corner, you can approach it in many ways. That depends on the ratio of triangles to P, what power of P is what T, so this is a complicated region. So all the analysis about sparse graphs is investigating this corner. And if P is small and T is large, when you go here, this is what clicks up here. And you have basically, this is for triangles, and if you have graph where vertex degree is d, then this thing just keeps moving. D equals 2, D equals 3, it just keeps shifting towards the diagonal. All this doesn't require any probability, it's just a clever analysis of the variation problem.
Can you say something more about why, whether it's a constant or not, is completely determined by h, the x minor end of hp of x to the 1/2, x to 1.
See, in general, one should expect constants, because the problem you want has to do with constants. You want to use something uniform. You're not specifying the triangle concentration to be different here, different there. You only care about the total concentration. So you would expect that the uniform is the best. And nearby that is true. The problem is non-linear, so this stability is only local, and you go far away, it's not true. I mean, that's interpretation after the fact. So basically, the you know the large deviation theory is well set up for this problem, and to really use it, one just need a Shimon-Radius lemma to sort of put it together. You can, any kind of questions you can answer. You can fix the number of triangles, the number of squares, whatever you want you can fix, and ask what will the graph look like. It's just a question of variation. You can't do any of them, but you can pose them.
You can't, yes, you cannot do anything with like more general embeddings like minors or something like that.
What?
Like minors, graph minors rather than just subgraphs. Homomorphism is basically accounting subgraphs.
Yeah. Exact computation. Exact computation is difficult. That's what I'm saying.
No, but like I'm saying, this theory, within this theory, you can't really pass the limit and so on, and counting sort of, I don't know, like some, this even makes sense. But like rather than just count homomorphisms, there may be other kinds of graph structures that you may wish to count.
Yeah.
Like
If it's something that's stable and
like under contractions, for example. Like, if you're not just allowing edge deletions, but you're allowing edge contractions as well. Whereas here you're only allowing edge deletions. When you ask for a particular structure, whether it is present in the graph or not. On the other hand, if you also allow edge contractions, and then ask whether after contracting is there a particular structure in there and how many different ways can you find it. That's probably not doable within this theory.
okay. I've not looked at them, so I have no opinion about that.
Okay, let's thank Gopal about it.